NASA has released more photos from the world's most powerful telescope, revealing the deep secrets of...
Scientists have discovered a large object hurtling through our solar system. It's only the third time a celestial body from beyond our solar system has been observed traveling through it.
The James Webb Space Telescope has once again altered our understanding of the cosmos by revealing astonishing new details about a celestial body known as R2 Swan. This object, initially classified as a comet, but later treated as an unusually active interstellar traveler, had already caught the attention of astronomers due to its erratic brightness and the expansive cloud of gas and dust it seemed to carry. What Webb has confirmed is that R2 Swan is far larger and more dynamic than earlier observations suggested, expanding the boundaries of what we thought possible for such an object drifting through our cosmic neighborhood. The discovery not only reshapes our view of this single celestial body, but also challenges some of the assumptions scientists have held about cometary formation, interstellar debris, and the building blocks of planetary systems. Before we start, smash the like and subscribe buttons for more updates. When R2 Swan was first spotted, its brightness was assumed to be caused by volatile ices, sublimating as the object neared the inner regions of the solar system. Telescopes on Earth tracked its coma, the vast cloud surrounding its icy core, and determined rough estimates of size, structure, and composition. Those early measurements made it seem like an ordinary comet, albeit one with an unusually energetic display. Now Webb's infrared capabilities have provided clarity that was not possible before. What we once thought was a modestly sized cometary nucleus is actually a body much larger than anticipated, cloaked in an even more expansive veil of molecular activity. Webb's imaging shows that R2 Swan's coma stretches out far beyond the previously calculated dimensions, dwarfing the expectations astronomers had when it was first cataloged. This revelation is remarkable because size directly influences a comet's capacity to endure its journey through the solar system. Smaller nuclei can fragment or disintegrate as they shed material under the influence of solar heating, while larger ones can maintain their structural integrity longer, releasing more volatile compounds over time. R2. Swan's unexpected size suggests that it is not just a fleeting visitor doomed to collapse quickly, but a massive, stable body capable of enduring repeated encounters with the sun's radiation. This resilience means its chemical inventory can be studied in greater depth, offering a pristine glimpse into materials that may predate the birth of our solar system. The confirmation of R2 Swan's size also brings implications for the debate about whether it is a true comet of our system or an interstellar interloper. Objects like Oumuamua and Borisov have already revealed that the galaxy is teeming with rocky and icy wanderers. If R2 Swan is indeed much larger than anticipated, it means that such interstellar visitors may not always be tiny fragments ejected from faraway systems, but could be substantial bodies, comparable in scale to the most massive comets we know. That possibility reframes how scientists consider the exchange of materials between star systems. A body as large as R2 Swan could, in theory, carry significant amounts of organic compounds across interstellar distances, potentially seeding young planetary systems with the chemistry necessary for life. Webb's instruments have not only confirmed the physical scale of R2 Swan, but also traced its chemical activity with unprecedented precision. The telescope's infrared spectrometers detected complex molecules streaming off the surface, including carbon-based compounds that hint at the object's primordial nature. These findings connect R2 Swan with the earliest phases of solar system formation, when volatile-rich objects bombarded the young Earth and likely contributed to the planet's oceans and atmosphere. By recognizing that R2 Swan is larger than expected, astronomers are also forced to acknowledge that its role in transporting these compounds across space is more significant than previously believed. It carries not just a whisper of ancient chemistry, but a veritable library of cosmic history encoded in its frozen core. The expansion of R2 Swan's estimated size challenges technical models as well. Orbital dynamics simulations had assumed a smaller body with less outgassing. Now, with Webb's revelations, astronomers must recalculate how such a massive active nucleus interacts with solar wind, gravitational fields, and radiation pressure. Its trajectory, which once seemed straightforward, may be subtly altered by the sheer force of the gases erupting from its surface. This means that predictions of its future path through the solar system will need revision, and spacecraft missions that aim to intercept such objects must adjust their expectations of the environments they will encounter. The broader implication is that cometary physics is far more varied than once thought, and each new observation adds complexity to the models designed to explain them. On a cultural and philosophical level, Webb's confirmation underscores how the universe still holds surprises in familiar phenomena. Comets have been observed for thousands of years, inspiring myth, fear, and fascination across civilizations. Yet with every technological leap in astronomy, they continue to defy easy categorization. R2 Swan, which seemed like just another bright comet at first, now stands as an example of how even well-known categories of celestial objects can surprise us with their scale and behavior. Its larger-than-expected size pushes humanity to acknowledge that our catalog of cosmic possibilities is incomplete, and that our exploration has barely scratched the surface. The sheer scale of R2 Swan also raises questions about its origin. If it is a native comet, then the reservoir from which it came, the distant Oort cloud, must contain bodies of similar or even greater dimensions. That would imply a far richer and more diverse population of icy worlds than previously assumed. If instead it is interstellar, then we are looking at a fragment of another planetary system, a survivor of processes beyond our sun's dominion, carrying the story of alien chemistry in its frozen heart. Either way, Webb's data forces astronomers to widen the scope of their theories about how and where such massive cometary bodies can form and persist. There is also a practical dimension to Webb's findings. Understanding the true size and structure of objects like R2 Swan has direct consequences for planetary defense strategies. While R2 Swan itself poses no threat, the principle remains. If a large icy body on a similar scale were on a collision course with Earth, it would represent an entirely different level of hazard than the smaller comets we have typically modeled. The ability to assess the size of such bodies accurately and early could be crucial for mitigation efforts in the future. Webb's role in providing that accuracy illustrates the telescope's value not only for pure science, but also for the long-term security of life on Earth. The grandeur of R2 Swan's true size also enriches the aesthetic wonder of astronomy. Images captured by Webb show an immense glowing cloud spreading across space, lit by sunlight scattering off dust and energized by volatile ices sublimating in plumes. For those who view these images, the scale evokes a sense of cosmic drama, reminding us of the raw, untamed forces that govern our solar system. This spectacle, while scientifically vital, also fuels the imagination, inspiring art, literature, and popular fascination with space. Discoveries like this connect the rigorous pursuit of knowledge with the human yearning for wonder. The confirmation of R2 Swan's unexpected immensity thus resonates on multiple levels: scientific, philosophical, practical, and cultural. It challenges scientific models of cometary activity, broadens our sense of what interstellar visitors can be, provides a richer laboratory for studying the chemistry of the early solar system, and deepens the mystery of cosmic origins. The James Webb Space Telescope, with its powerful instruments, has illuminated another hidden truth about the universe, proving once more that every answer it provides opens the door to new and profound questions. In confirming that R2 Swan is much bigger than we thought, Webb has not just expanded our knowledge of a single object, but has expanded our sense of the universe itself, vast and layered with secrets that only the most powerful tools can uncover. The James Webb Space Telescope's confirmation that R2 Swan is significantly larger than previous measurements suggested is not just a numerical correction in astronomical records. It is a profound shift that invites a deeper exploration into how such bodies come to exist, evolve, and influence their surroundings. The magnitude of this revelation extends far beyond simply categorizing an object. It forces us to confront new questions about the architecture of planetary systems, the scale of cometary bodies, and the mechanisms that drive their activity across space. One of the most fascinating aspects of Webb's confirmation is how it compels astronomers to reassess the birthplaces of such large cometary objects. If R2 Swan is indeed a member of our solar system, its origins likely trace back to the Oort cloud, a theoretical shell of icy bodies surrounding the solar system at immense distances. For decades, the Oort cloud has remained an elusive idea, supported by indirect evidence rather than direct observation. The existence of a body as large as R2 Swan lends weight to the argument that the Oort cloud may harbor giant icy bodies, some rivaling dwarf planets in size. This shifts the Oort cloud from being viewed as a diffuse and scattered reservoir of small comets to a possible storehouse of much larger and more complex objects. Such a revision would reshape our mental picture of the solar system's outermost frontier. If, on the other hand, R2 Swan proves to be interstellar in origin, the implications become even more profound. It would suggest that other star systems, much like our own, can forge and eject massive icy wanderers into the void. These bodies, hurtling through interstellar space, could carry not only the materials of their home systems, but also insights into the processes that shape them. Webb's ability to detect and analyze such a body means that we now have a window into alien chemistry and planetary formation mechanisms. The scale of R2 Swan ensures that its composition is more complete and diverse than that of smaller fragments, making it an extraordinary messenger from beyond our solar system. Understanding the sheer size of R2 Swan also provides a new lens on the role of comets in planetary formation. In the early days of the solar system, impacts from large icy bodies like this would have been pivotal in shaping planets, delivering volatiles such as water and carbon dioxide to their surfaces. Earth itself may owe much of its oceans to bombardments from massive comets. If R2 Swan is far larger than expected, it suggests that the population of such influential impactors could be greater than previously thought. This possibility redefines how we think about the habitability of planets, not just in our system but across the galaxy. Worlds orbiting other stars may also have been shaped by encounters with giant comets, making them more likely to host conditions favorable to life. The confirmation of its scale has also re-energized discussions about the internal structure of comets. Are bodies like R2 Swan uniform chunks of ice and rock, or are they more complex, layered relics of primordial matter? The fact that Webb has revealed such an unexpectedly large nucleus suggests the latter possibility. Larger cometary bodies could preserve more intricate stratifications, with alternating layers of frozen gases, dust, and organic molecules accumulated over eons. Studying such layers could offer a record of conditions in the early solar system, preserved like tree rings frozen in time. If future missions could probe R2 Swan up close, the insights into cosmic history would be immeasurable. Webb's ability to distinguish the composition of R2 Swan's coma provides another dimension to the story. The gases streaming from its surface are not random. They follow patterns that reveal both the thermal history of the object and the distribution of ices within it. A larger nucleus means a larger variety of ices can exist, each sublimating at different distances from the Sun. This variety could help astronomers understand the dynamics of cometary activity more broadly. For instance, smaller comets may only display water vapor and simple molecules, while a massive comet like R2 Swan could harbor exotic compounds, from complex hydrocarbons to rare isotopes. Such a discovery broadens the chemical library available for study, enriching our knowledge of the materials that can give rise to life. This chemical richness also raises questions about the potential role of comets as carriers of prebiotic material. If R2 Swan contains complex carbon-based molecules, it stands as a testament to how life's raw ingredients can be preserved and transported across billions of years. The scale of its nucleus implies that it could carry immense quantities of these compounds, suggesting that similar comets may have delivered vast chemical payloads to young planets across the galaxy. Webb's confirmation of its size makes this prospect even more exciting, transforming R2 Swan into a potential example of panspermia in action, the cosmic dispersal of life's essential chemistry. Another implication of R2 Swan's size lies in the mechanics of its outgassing and the dramatic tails it produces. The immense surface area of a larger nucleus provides a more powerful engine for driving jets of gas and dust into space. This leads to more spectacular displays. But it also complicates the physics of how comets interact with solar wind and magnetic fields. The tails of comets are not simple streaks of material. They are dynamic structures shaped by complex interactions with solar particles. With a comet as large as R2 Swan, those interactions take place on a much grander scale, offering a natural laboratory for studying plasma physics in space. The data collected from Webb's observations could refine our understanding of these interactions, which also apply to phenomena like planetary magnetospheres and stellar winds. The discovery also reshapes how we think about the long-term survival of comets. Smaller comets can burn out or fragment within a few passes near the Sun. A comet of R2 Swan's dimensions, however, could remain active for much longer, surviving repeated journeys through the inner solar system. This durability means that some comets may act as long-lived participants in the solar system's evolution, influencing planetary surfaces and atmospheres across geological timescales. By recognizing that R2 Swan is much bigger than anticipated, scientists are acknowledging that some comets may play roles in planetary evolution that stretch over eons. From a technological standpoint, Webb's achievement demonstrates the unmatched power of infrared astronomy. Previous telescopes could only approximate R2 Swan's size by estimating its brightness, a method prone to error when dust and gas obscure the nucleus. Webb, with its sensitive infrared instruments, could peer through that veil and measure the thermal radiation directly, providing a far more accurate picture of its true scale. This milestone underscores how advancements in technology continually reshape our understanding of the universe. It also hints at the discoveries yet to come as Webb continues to apply its unparalleled capabilities to other comets, asteroids, and interstellar visitors. The scale of R2 Swan also invites consideration of what it would mean for future exploration. Spacecraft have already visited several comets, such as Halley, Tempel 1, and 67P/Churyumov-Gerasimenko. But a body the size of R2 Swan presents an entirely different kind of target. Its immense gravity, relative to smaller comets, could allow for more stable orbiting by spacecraft. Its vast inventory of volatiles could offer insights into dozens of chemical processes. A dedicated mission to such a comet could revolutionize our understanding of icy bodies in ways that smaller comets never could. With Webb confirming that these giant comets exist, space agencies may consider prioritizing such missions in the future. The confirmation of R2 Swan's larger size also fuels the imagination about potential human interactions with comets. While it remains firmly in the realm of speculation, the idea of harvesting cometary materials for fuel, water, or even construction resources has been discussed in scientific circles. A massive comet like R2 Swan, laden with ices and minerals, could one day serve as a resource depot for future spacefarers. The larger the nucleus, the more practical such resource extraction becomes. While humanity is not yet ready to undertake such endeavors, Webb's discovery nudges these ideas closer to feasibility by proving that such massive reservoirs of material are indeed drifting within reach. On a broader level, R2 Swan's immense size redefines our sense of scale in the solar system. We often think of comets as fragile, ephemeral visitors, brief flashes of light across the night sky. To learn that some of them are colossal bodies capable of rivaling mountains or small planets in their dimensions forces us to recalibrate our sense of cosmic proportion. It highlights the fact that the solar system is populated not only by planets and moons, but also by titanic wanderers, whose influence can be profound. These revelations remind us that the solar system is not a static arrangement of neatly ordered worlds, but a dynamic, evolving environment filled with surprises. The implications extend even to the cultural and symbolic significance of comets. Throughout history, comets were seen as omens heralding change or upheaval. With Webb's revelation, comets like R2 Swan take on a new symbolism. They are not just fleeting phenomena, but substantial bodies with deep histories. Their unexpected immensity speaks to the richness and unpredictability of the cosmos. For the human imagination, this deepens the metaphorical power of comets, transforming them from signs of fate into symbols of discovery and endurance. R2 Swan's true scale also highlights the importance of international collaboration in space science. Observatories across Earth first noticed and tracked the comet, but only Webb's advanced technology, positioned in space, could reveal its full dimensions. This partnership between ground-based and space-based astronomy shows how humanity's greatest discoveries are made when we pool resources and knowledge. Going forward, as Webb identifies more oversized comets, ground-based observatories will play a vital role in monitoring their paths, activity, and evolution, ensuring a comprehensive picture. Webb's confirmation of R2 Swan's size underscores an enduring truth. Every discovery in astronomy is both an answer and a beginning. By revealing the unexpected immensity of R2 Swan, Webb has not closed a chapter but opened many. questions now abound. How many other comets of similar size exist? What does this mean for the diversity of bodies in the Oort cloud? Could interstellar comets of this scale be common, ferrying materials across galaxies? Each of these questions is vast enough to inspire years of research, missions, and debate. R2 Swan's confirmation as a much larger body than astronomers initially believed pushes our understanding of comets and icy wanderers into bold new territory. But the implications do not end with size and chemistry alone. What makes this discovery so important is the way it reshapes multiple scientific disciplines simultaneously, opening new frontiers in planetary science, astrophysics, cosmochemistry, and even the strategies humanity may one day use for exploration and survival in space. One of the most striking consequences of Webb's findings is the impact on theories of gravitational capture and orbital evolution. Comets like R2 Swan are not just passive travelers through the solar system, they interact dynamically with the Sun, planets, and smaller bodies they encounter. A nucleus of greater size implies significantly more mass, which in turn changes how gravitational tugs from Jupiter, Saturn, and other planets could affect its long-term orbit. Instead of being a temporary visitor, it is possible that a massive object like R2 Swan might remain bound within the solar system for far longer, its trajectory stabilized by its own inertia. This introduces a new category of cometary behavior, giant comets that become quasi-permanent members of the planetary system. Such a realization reshapes how astronomers think about the exchange of material between inner and outer regions, as well as the ways giant planets sculpt the paths of icy wanderers. Another area of research invigorated by Webb's confirmation is the study of isotopic ratios. Comets have long been studied as archives of the early solar system, and isotopic fingerprints, such as the ratios of deuterium to hydrogen in water molecules, help scientists determine their place of origin. With R2 Swan being so much larger than expected, it offers an unprecedented reservoir of isotopic information. The diversity of isotopes across different layers of ice within such a large nucleus could reveal whether it formed in the cold outer reaches of our system, or whether it carries the more alien signature of interstellar birth. Such data would allow scientists to map not just the history of this particular comet, but the broader distribution of volatiles in space, building a comparative record across multiple systems. Equally compelling is the role that R2 Swan's immense size plays in shielding and preserving organic material. Smaller comets, constantly battered by radiation and solar heat, quickly lose their more fragile compounds. But a massive cometary nucleus can act as a vault, burying layers of organic material beneath kilometers of ice. Webb's instruments hint that such compounds exist within R2 Swan, and the larger its size, the greater the likelihood that some of these have remained unaltered since their formation billions of years ago. The possibility that such a body may be harboring pristine organic chemistry untouched since before the solar system's birth is extraordinary. For astrobiologists, this means access to a record of molecular evolution that may shed light on how the precursors to life assemble naturally in space. The discovery also has fascinating implications for space weathering processes. Comets are exposed to cosmic rays, solar radiation, and micrometeorite impacts over vast stretches of time. On a smaller body, these interactions can reshape or even obliterate surface features within relatively short cosmic timescales. But with a massive comet like R2 Swan, new dynamics emerge. Its gravity can retain more of the ejected dust, recycling it into the coma. Its size means that only its outer layers are significantly altered, while its core remains well protected. This difference gives scientists a natural laboratory for comparing how space weathering affects small versus large icy bodies, leading to better predictive models of how surfaces evolve across different environments in the solar system. Webb's confirmation also speaks to the question of cometary fragmentation. Astronomers have long observed that some comets, particularly during close passes to the Sun, split apart dramatically, producing multiple smaller fragments. Understanding whether R2 Swan could undergo such a fate requires reconsidering fragmentation thresholds. A nucleus of this unexpected magnitude might resist breaking apart under stresses that would shatter smaller comets. However, should it ever fragment, the resulting pieces would themselves be significant in scale, potentially producing a swarm of large daughter comets. This theoretical possibility forces astronomers to model how giant comets might contribute to episodic influxes of debris into the inner solar system, events that could influence planetary climates and even trigger mass extinctions under certain circumstances. Beyond pure science, Webb's revelation influences how we envision the practicalities of deep space navigation. For spacecraft traveling through the solar system, large comets represent not only hazards, but also opportunities. Their massive comae create regions of dense particle environments that can interfere with instruments or cause physical damage. At the same time, they also serve as navigational markers, glowing beacons visible across vast distances. A comet the scale of R2 Swan could one day function as a natural checkpoint for spacecraft traversing the outer solar system. Its brightness and predictability may make it a natural rendezvous point for probes heading toward more distant targets, such as Neptune, Pluto, or even interstellar space. The size of R2 Swan also reopens the conversation about planetary migration in the early solar system. One leading theory of solar system evolution, known as the NICE model, proposes that the giant planets shifted dramatically from their original orbits, scattering countless icy bodies outward to form the Kuiper Belt and Oort cloud. If large comets like R2 Swan exist in greater numbers than expected, this suggests that the process of scattering preserved not only small debris, but also giant icy remnants. This would strengthen the case that planetary migration was a chaotic, large-scale event, capable of tossing planet-sized fragments across vast distances. Such a narrative connects the story of R2 Swan to the very architecture of our solar system, offering a fossilized clue to one of its most violent and formative eras. Webb's ability to confirm R2 Swan's scale also serves as a test for future observational methods. As astronomers prepare for next-generation instruments such as the Nancy Grace Roman Space Telescope and ground-based observatories like the Extremely Large Telescope, Webb's work establishes a benchmark. It demonstrates how precision infrared measurements can penetrate dusty coma and resolve the thermal signatures of nuclei. This success sets the stage for even broader surveys of comets, asteroids, and interstellar objects. With better technology, humanity may soon catalog dozens of R2 Swan-like giants, creating a population map that could revolutionize our understanding of the icy outer solar system. The educational impact of this discovery is equally significant. Comets already hold a special place in public imagination, and the idea that one is far larger and more complex than once believed creates a compelling narrative for science communication. Teachers, museums, and planetariums now have a fresh story to tell, that our universe still holds surprises even in objects we thought we understood. R2 Swan becomes a tangible example of how technology like Webb transforms knowledge and how curiosity drives discovery. Inspiring the next generation of scientists depends on moments like this, when a single finding can capture imagination while demonstrating the rigor of modern science. R2 Swan's newfound scale even intersects with questions of planetary defense. Although it is not a threat to Earth, its existence underscores the need for accurate size assessments of near-Earth objects. A body misjudged by a factor of 2 or 3 in diameter, as R2 Swan was, could translate into a catastrophic underestimation of impact energy. Webb's revelation demonstrates how easy it is to underestimate such objects when relying solely on optical brightness, and how crucial it is to integrate infrared observations into defense strategies. This fusion of scientific curiosity and practical necessity illustrates the dual role of astronomy, not only expanding knowledge, but also safeguarding our future. Another dimension worth exploring is how giant comets affect planetary atmospheres during close passes. As they shed enormous amounts of gas and dust, these materials can interact with magnetic fields in upper atmospheres, creating auroras, temporary chemical imbalances, or localized heating. On Earth, such interactions are minimal, but for smaller planets or moons with tenuous atmospheres, a close encounter with a massive comet like R2 Swan could be transformative. This raises the possibility that throughout history, large comets have not only delivered volatiles, but also temporarily altered the chemistry and climate of planets they passed near. Webb's data, showing the sheer quantity of material R2 Swan releases, strengthens the plausibility of such scenarios. The scale of R2 Swan also adds weight to comparative studies of other giant comets, such as C-2014 UN 271 Bernardinelli-Bernstein, which was hailed as one of the largest comets ever discovered. By placing R2 Swan in this category, astronomers can build comparative profiles of these enormous icy bodies. Are they common remnants of planetary formation? Do they share similar compositions, or are they highly variable? Such comparisons allow scientists to build taxonomies much as they do for asteroids or exoplanets, creating frameworks that bring order to what might otherwise appear as random cosmic wanderers. Speculation also arises about what secrets may lie beneath R2 Swan's icy crust. Could it harbor subsurface oceans, like those suspected on moons such as Europa or Enceladus? While the heat and energy available within a comet are far less than those on moons orbiting giant planets, the possibility cannot be dismissed entirely. Internal heating from radioactive decay, combined with insulation provided by its massive size, could create pockets of liquid water deep within. If such reservoirs exist, they might offer microenvironments for chemical evolution, even if not for life itself. This line of inquiry blurs the boundaries between comets and icy moons, highlighting the continuum of icy worlds that populate the cosmos. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on R2 Swan's surprising size discovery by James Webb? We want to hear from you. Thank you for watching, and see you next time.